So today we're going to continue with sensors, and we're on two-wire sensors. And we talked about negative thermal coefficient thermistors last time, and we looked at the series circuit that they're built in. And we're going to start off today with permanent magnet sensors. And permanent magnet sensors are used to measure the speed of a rotating component. Permanent magnet sensors are a little bit different, and that they generate their own voltage. They don't need voltage applied to them. So although we will see a plus and a minus on a wiring schematic going to them, that's not power and ground going to the actual sensor. That's actually what the signal will look like coming back from the sensor. And we need to test both wires and can test both wires. So it consists of a permanent magnet surrounded by a winding of wire. When a metallic, iron or steel, is passed extremely close to a magnet, the magnetic field is interrupted and a small amount of AC voltage is induced into the windings. The induced voltage amount varies by the speed of the interruption, the distance between the magnet and the metallic object, and the strength of the magnet. So the strength of the magnet is the magnet in the sensor. So therefore, buying a factory sensor that may cost 40 bucks might be a better option than buying an aftermarket sensor that costs 11 bucks, because there's probably some difference in the magnet, which will equate to some difference in the performance of the sensor. The distance between the magnet and the metallic object is very important. So when we replace these sensors, we need to make sure the mounting surface is clean and they're installed properly. Many times people have issues because of dirt and age and corrosion. When they replace one of these sensors, they don't get it installed all the way or seated correctly. And then they're still getting the same code or the same problem, even though they've got a new sensor, even a dealer sensor in place. It's because the distance is too far away, so we're not generating that electrical magnetic field. These sensors, the signal that they create changes by the speed of the interruption and is affected by the distance. So once I set the distance, that's going to tell me if I get a signal or not above a certain speed. So I need to have that speed interruption happening fairly quickly. So these sensors will not measure low speed movement, only higher speed movement, which is one reason why we can't use them on something that slides, because by the time it slid, we won't have induced a voltage enough of a signal for it to see detail. So these sensors are pretty good at seeing detail at 50 miles an hour, for example, or at 1,000 RPM, 1,000 revolutions a minute. They're not good at seeing something that happens at 30 revolutions a minute. They won't see it. So or see it very little. So that is where we run into. So I do have a lab that I'm going to turn on speed and position sensors. I'll probably turn that on later on today if we get into three-wire sensors. If not, I'll turn it on tomorrow. Actually, I'll probably turn it on today anyways. But it's on speed and position sensor lab. And I show you 4 different kinds of sensors and show you how they look on a lab scope and the differences between them. And that goes back to what we're talking about in our PowerPoint presentation. So I said these generate an AC signal. So this is our AC signal right here. This is also an AC signal right here. So at low speed, we have low amplitude, which is our height, and a low frequency. So it takes from here all the way to here to go through 1 cycle or 1 hertz. At higher speed, I get more amplitude, more height, plus now I've gone through 1 hertz or 1 frequency just between here and here. So I got 1, 2, 3, and 3/4. So I'm going 3 3/4 times faster. I'm spinning 3 3/4 times faster, which means that my frequency increased, but so did my amplitude, the strength of the signal. So since this is an analog signal, the computer has to convert this into ones and zeros. So it takes a certain amount of amplitude, a certain amount of movement off of that 0 line before it's going to constitute a 1, or on the other end, a 0. So if the line's just doing this, the computer won't recognize that. It needs to see enough of amplitude, both positive and negative, so it can count the hertz. And so many times we see this on a scan tool displayed in hertz. If we're looking at more of the raw data, or we look at the interpreted data, vehicle speed, wheel speed, transmission input, output speed, things like that. So these are primarily used for the things you see here. Camshaft position, crankshaft position sensors, wheel speed, vehicle speed, and transmission input and output sensors. So we can see here we have two wires, actually one wire, but two ends of it wrapped around a metal housing, and there's our reluctor wheel. And as this spins, we're going to generate a signal, and the signal is generated right here, and that's what we would see on a lab scope. Now, some of these, such as Ford, instead of being on 0 volts, actually use 3 volts. They put DC voltage on the line and then float the AC signal on top of that DC voltage. And the computer uses that DC voltage for, fault recognition and so on. So although this is an AC signal, if I'm looking at it on a scope, I'm going to use a DC setting. And that allows me to see the entire waveform. It's also going to tell me if it's at 0 or if it's at 3 volts or somewhere else. So it's gonna let me know the whole picture. If I'm just on AC, all I'm going to see is the waveform and the amount it changes off the 0 point of the waveform, but I have no idea if that's really 0 volts or not. So it's kind of counterintuitive, but we actually use a DC scale on a scope to measure our AC signals because it's more accurate for what we need to do, given how they design computer systems. So here's a sensor on the car. It's a crank position sensor. And so we can see there's 2 wires right here. And here is our reluctor ring. So if I want to test this, I would back probe here or both and attach my scope and get a signal. So I would normally go between one of these and ground. They normally want me to go between the positive lead and ground because then the signal is going to match the pretty picture they give me in the information. But if I go on the other one, it's still going to tell me if it works, just the picture won't, it would be kind of inverted from what the documentation shows. But I can still get that. So a lot of times these are kind of hard to get to or hard to see. I'm really just looking, does it make a signal? That's why I say I may even plug into both and hook use 2 channels on the scope and make sure I'm getting something out on each of them. But here's a wiring schematic for this. So you can see I have sensor low and signal low, signal high. A lot of times we see cam plus and cam minus or crank plus and crank minus, which is really confusing to people because they think there should be power there or there should be ground there. No, it's just showing the polarity of the signal that's being generated. This is a shield wire, so this is not part of the circuit, but because this is an AC signal with pretty low amplitude, we're going to put a ground around the outside of it to allow for some shielding so we can get a clean signal back to the computer without a lot of electromagnetic interference. Because if you notice back here on this picture, actually I'll show you on the next one, we're really not moving that far up and down in voltage. So here is a scope pattern. And we can see here that we are on the voltage scale, 10 volt scale, and I'm on DC. So if you notice, my 0 volts is all the way down here. The center of the line is up here. More what about 1.75 volts, something like that. So clearly a bias voltage, a DC bias voltage on the line. So the question is that normal? Is that supposed to be there? Or is that an issue? And that's where the service information comes in. In this case, this is a known good. If you notice, I have a nice consistent signal, and then I come down and I miss something. And then I actually get a higher spike here, and then I come back down and go back to normal. This right here is what we call a TDC indicator. So this lets the computer know where top dead center on number 1 cylinder is. So when is the piston on number 1 cylinder at top dead center on the compression stroke? That's what that tells the computer. Now this signal may not be at top dead center. It can be 50 degrees before, 60 degrees before, whatever. And most of the time it is before, because it's telling the computer, hey, start your clock because here's what's coming up. So you can make, ignition timing, fuel, other decisions you need to make. This is caused by a missing tooth. So this particular vehicle has 58 teeth with 2 spaces missing. So normally you'd have 60 teeth. So each tooth would be 6 degrees for 360 degrees. And what they're doing is they're taking 2 teeth out. So then you got 58 and 2. So that's a pretty common. Some manufacturers just take 1 tooth out. They use different numbers for that. But the concept of what manufacturers do is the computer needs to know where top dead center is for number 1 cylinder. Now, if I'm just looking at the crank sensor, that can be either top dead center of my compression stroke or top dead center of my exhaust stroke. It's going to look the same on the crank sensor. That's why if I need to know which one's compression, which one's exhaust, I would need to use a camshaft sensor. So I would use both sensors. So this right here is an analog sensor. We also use some digital sensors, which are Hall effect sensors, which we'll look at. And we'll see those in the 3-wire section. But in the old days, if I thought that I had an engine that was out of time, meaning my relationship between my crankshaft and my camshaft, something was off, something wasn't where it should be, like a bad timing chain or a bad gear, I would have to disassemble the engine in order to find that. Now with sensors, I may no longer need to do that. So in this capture right here, again, another scope capture, right? Time and amplitude. And I'm looking at 3 signals here. So here's a crankshaft sensor. So there's my top dead sensor signal. My crankshaft went completely around. Again, went completely around. Again. So each of these is 360 degrees of crankshaft. My crankshaft's gone completely around. Up here is my camshaft. And my camshaft goes around at half the speed of my crankshaft. So it's gone around once between here and here. And if I look up in the service information, I will see where this signal should align with this signal and how many of these over. So I can actually see, and again, each of these is about every 6 degrees. So I can get an idea pretty close of where I'm at. And 1 tooth is about 19 degrees. So it's pretty obvious when something's bad. This other signal right here is my ignition that we're firing for the cylinder, in this case, number 1 cylinder, and here's where we're actually firing the ignition. And I can see how my ignition relates to the position of my engine, and I'm actually firing the ignition slightly before top dead center, which is common. We normally time engines before top dead center. So you can see where we can kind of start putting these pieces together, these sensors, and that's why this is so important, is to understand not only what type of sensor I have just by looking at it, like right here, that this is a crank sensor, but also knowing what this slot here means and understanding it's telling the computer where top dead center is and that slot is not necessarily where top dead center is. In other words, if I want a computer to set the ignition timing for the correct timing, I would need to know when that event's happening before it happens. So I'd want to have something telling the computer before it gets there, right? Because if I told it, oh yeah, you just passed, right? It's like driving down the road. Oh, you just passed the road. That doesn't help much. What you need to know is, oh, the road's coming up at the next corner. Well, the same thing that's true with directions is the same thing that's true with a computer system. Our computer system needs to know what's coming. So even though the book says this is at top dead center, it's wrong. It's a top dead center indicator. It is not where top dead center is in almost all cases. Like anything with cars, there seems to be an exception to almost everything. So a permanent magnet sensor could be used to measure which of the following? One, absolutely. Crankshaft rotation. So position sensor, vehicle speed position sensor, although most vehicle speed position sensors are mounted in the differential, performs well performs a very different function for the powertrain control module than the crankshaft sensor. Electrically, it's exactly the same. So it is exactly the same as a crankshaft sensor. Permanent magnet sensor is a permanent magnet sensor. I don't care what we call it. We're going to test it the same. The only difference between this position sensor, or the only real difference between this position sensor and a crank sensor, is that I will not see that separator signal. I will not see that missing tooth on a wheel speed sensor or an ABS sensor, because I don't care when the valve stem comes around. I don't care, how many times it's rotating as far as where it actually went around. I'm looking at the speed of rotation. So I don't need that starting point. So that's a difference on the trigger, not a difference on the sensor. So these are all tested the same way. So if you're testing a permanent magnet sensor, it makes no difference what its function is once you understand its operation. And that's really the key here, because we use, the same types of sensors all over the vehicle, and we call them a lot of different things. I mean, for example, this particular sensor, I could unplug the wire connector. I could plug my scope into just these two things, rotate the sensor, and I would see a signal back on my scope. So that is, actually I need to plug in ground for a reference and then plug into those, but I would see a signal come back on the scope. And that's one of the neat things about these sensors. They generate their own signals, so I don't need to do that. And I'll demonstrate that on the lab. So here's a wheel speed sensor. Again, a control unit sensor looks different. We have a couple different types of sensors, but here's a permanent magnet right here. Again, where we're generating back that signal. So whether I know quite a few of you have already had the brakes class, so you should be familiar with these wheel speed sensors and differential speed sensors, because I know they're covered there. But a permanent magnet sensor is a permanent magnet sensor. I don't care what task we ask it to do. It's like a thermometer. Is an oven thermometer really that different than the thermometer on the wall, or a freezer thermometer, or the thermometer you use to check your temperature, or any of the other uses we have for a thermometer? Or is it, once you understand how to read a thermometer, it doesn't really matter where I put it? I don't think anyone would be intimidated by, I don't know how to use a thermometer because it's in the freezer and I've never looked at one there. At least I hope not. So that's the same thing I'm talking about here. I'm talking about the commonality. Once we understand how the component works and what it doesn't matter where we put it or what we call it, because we know how it works. What kind of electrical signal is created by a permanent magnet sensor?
Analog.
Analog, number 2, absolutely.
Sorry, Brian, someone's enjoying their breakfast. If you wouldn't mind muting everybody, thanks.
Yeah, I can't see who that is. Oh, I can see. All right, got it.
Appreciate it.
Not a problem. So a pressure switch. Again, 2-wire, normally 2-wire. On-off switch located in a location where fluid pressure monitoring is critical. So common uses are for air conditioning, power steering, engine oil. This is not a variable resistor, but an open-closed switch. So depending on the engineer's design of the circuit, the switch may either be open or closed in the rest position. So the wiring schematic will give us a clue for that. So by looking at the wiring schematic like I am here, I can see I have a power steering pressure switch. It is in its normal or default position is open. So when it gets excessive pressure, the switch will close, which means that I should have ground here and I should not have ground here until the switch closes. Then I'd see this side switch to ground. So I can put a digital multimeter right on here and turn the steering wheel all the way to one side where it kind of makes that noise, which would generate enough pressure to kick the switch, and see if I get ground here now. Ground is not 0 voltage. So if I'm testing this and I'm testing for ground through the switch, I would want to hook up the positive lead of my voltmeter to battery positive and the negative lead of my voltmeter to number 1, because I'm actually checking for ground. I'm not looking for no voltage. All right, that we talked about this in electrical. I mean, this is a important distinction. So I can see that in one position, these two should be different. In the other position, they should be what? Electrically the same. So typical switch, and this is true whether we're talking oil pressure, AC pressure, or in this case, power steering pressure. And so pretty simple series circuit. We know if this is ground, this would be the power side of the circuit. So I may see some power come down here where they may put some power on that line through a resistor just for fault detection or so they can see the change of the circuit, or they may not. That depends on the manufacturer and how they design their computer. But I do know that I would have ground at number 2 all the time, and I should get ground at number 1 when I have pressure.
So when you're reversing the leads like that, you should, are you looking for like 0 voltage because the voltage you want to be basically no difference in voltage potential on the ground side?
Right. So when I reverse the leads like this, so when I'm hooking the positive lead to the battery and the negative lead here, I would see 0 voltage with the switch open. And as soon as the switch closes, then I'd see 12 volts on my meter, indicating that that's a good ground. And the other lead of my meter is on battery positive.
Got it.
Yeah, because if I did it the other way, if I went to battery negative and put the positive lead here, I might see nothing and then nothing, because nothing's going to change. One is just like holding my lead out here, you know, in the air, and the other one is now it's touched the ground. Well, the meter doesn't know the difference between those two things. That's why we would hook our meter up. So so the meter is going to show us the change of the switch.
Got it.
And you can see how looking at the schematic allows us to come up with a test plan without reading through all these, you know, all this documentation. As soon as we understand that it's a switch and understand what it's measuring, we know that it, you know, normal situation, low pressure, it's going to be open, and at high pressure, it's going to be closed. And I just have to figure out how to make high pressure. And on steering, that's easy. Turn it to the steering lock. So, you know, different systems are like that. It's like our AC, right? Our AC, we have different pressure switches for low pressure and for high pressure. Well, the low pressure switch will keep the AC compressor from running. So if the system's empty, the low pressure switch would be open. If it has some stuff in it, then it'll be closed and allow the compressor to come on. So if the compressor is not coming on, I can always just disconnect the switch and put a jumper wire across it so the compressor comes on, and then see if it gets cold. If it gets cold, I got a bad switch. If it doesn't get cold, then I've got an empty system. So that's something we do all the time when diagnosing switches on AC systems, because the switches, especially old ones, used to go bad all the time. And I used to keep a jumper right with my AC stuff just for doing that. It was something we did all the time because it was a quick way of diagnosing it on which way to go with it. So here we can see the pressure switch on the power steering hose. And I chose power steering pressure switch here because that's an input for our computer, because our computer needs to know, or may need to know, depending on how the engineers designed it, if I am applying excessive force to my power steering system, because that's going to put additional drag on my engine. So think about if I have a small engine and they're getting smaller. So can I run the AC at the AC compressor at the same time we have the wheel crank? Maybe I need to turn off the AC compressor. Maybe I need to adjust the engine speed up so we don't stall the engine. Maybe if the AC compressor is off, I don't want to turn it back on while this is going on, because if you're at low speed and your steering wheel's cranked, I don't want to turn the AC compressor on when you're trying to park the car. I don't want to run the engine speed up suddenly while you're trying to park the car, because it might lurch forward, cause an accident. So you know, this technology has been around for well over 20 years that we've been using pressure switches, different manufacturers have, as part of their idle control systems to make sure that when you're parking the car, not only does the car not fatigue and stall, but it doesn't lurch forward. So that's just an example of why we would use that power steering pressure switch. A switch will produce a voltage change in the circuit when it opens and closes. Is that true or false?
True.
True, absolutely. So here's our fuel tank sending unit. So this is a rheostat. And how it works is this is a series circuit with two resistors. One is in the gauge, the other is in the fuel tank, which is a rheostat. Now on newer vehicles, we now have computer controlled gauges. So instead of a gauge here, we're going to have a module, and the module is going to have a fixed internal resistor, very similar to the circuit on our NTC thermistors, where we had a variable resistor that changed with temperature and a fixed resistor inside. And we divided the voltage on the circuit between the two loads in the series circuit and measured the voltage in the middle. So on a newer system, that's what we're doing, even though we're still using a rheostat. So what this does is, depending on the amount of fuel in the tank, so say it's full, I'm going to move all the way over to here. Well, if I'm up here, I'm going to have ground. I'm going through very little resistance before I go to the arrow. Go over here. So I would drop most of my resistance here, which gives most of the voltage here. And I would have high current flow through this wire, which actually heats the element inside the gauge and causes the needle to deflect and go to full. When I go to empty and I'm over here, now I have ground and I go through a lot of resistance before I finally get to come up here, which means less current flow. And with less current flow, there's going to be less of a voltage drop on this resistor, less heat generated because it's using less voltage, less deflection of the needle, and we now read empty. So that is how these work. The gauge part works the same way, whether I'm talking about an oil pressure gauge or a coolant temperature gauge. The difference is, what's my sensor, right? So the difference is just in how we're changing that current flow. So again, this is a reset. So very simple. So basically, we're just changing the amount of resistance. Instead of using a variable resistor, we're changing the contact point along a fixed resistor to change how much of this resistor we're using, which changes the amount of current flow, which changes the voltage on the wire between the two, which means the voltage drop across the gauge to ignition is going to change. The higher the voltage drop, the higher the needle reach. So to test these systems, what we do is we disconnect the wire right here. And with it disconnected, I should read empty. And when I ground it, we should read full. If it reads full when it's grounded and empty when it's not grounded, then it needs a new sending unit. If the gauge goes, instead of going to full, goes way, way, way too far, that's a gauge issue. So sometimes gauges will go out of cal. The resistance inside the gauge has a problem. So therefore, it is deflecting the needle too far. Some gauges have some adjustments on them that you could do. Real fine little screwdriver adjustment, like eyeglass screwdriver type thing. Or they go out. So a lot of gauges have stops to kind of prevent the gauge from wrapping, but I have seen them go. It's not uncommon to see them go a little bit out of the normal range. And there is some specifications. I know, Tim, you had mentioned this on your gauge. I actually have some resistance specifications for your old Ford on what it should read at different levels. So let me go grab, let's see, where is that?
Can I ask a quick question before you go to that? Because I totally want to hear about that. But something stuck in my head here. So in the book, in one of these chapters, I think it was an electrical that we got to, but we didn't touch on it in the class. But at the very end of these chapters, they talk about gauges.
Yes.
And they talk about the gauges with windings and basically the magnetic, as the current, I guess, increases or decreases through windings on either side of the needle, it attracts it one way or the other through magnetism. is that a less common or not common? Why is it? I noticed we didn't talk about it at all. The book talked about it, and I thought, oh, that's how the gauge works. But this is how the gauge works.
This is how the gauge works, and this is pretty universal. They have some 2 and 3 wire gauges, so they do have some 3 wire ones that do kind of split it inside, and based on the strength of the magnetic field, it's going to pull it more one way or the other. But we really don't see that, and from a diagnostic standpoint, it's really kind of a non-issue.
All right, I'm gonna dump that then. Forget it.
Yeah.
Okay.
So, and the
Thanks.
book kind of gets, the book leaves some stuff out that is pretty common. And then they like dig real deep into things that were used once 40 years ago. And I don't understand that, Let me grab my keys real quick because I want to go grab a tool and a chart to show you guys.
Cool.
But the old gauges with the resistor.
Okay, so I have a little instrument gauge tester that I bought a number of years ago, and it came with a chart in it. Open up for me. That's weird. I don't know why the little top's not opening up. So it is a variable resistance block, and it has 4 dials on it. And these dials are hooked in series, and one is ones, tens, hundreds, and thousands. So I can adjust these to put a certain amount of resistance in series. And then it has a set of leads that connect to my between ground and my gauge wire. So then I can actually do this to move the gauge on. So I use this for sensors. I use it for other things that I'm doing. And I came with a chart, and this chart's pretty old. Not as old as I thought. It goes all the way to 94. So it's newer than I thought. And if I look here at Ford, Chrysler Ford Motor Company, and going back to your question, they break it down to metallic and bimetallic gauges going back in 62 to 72, Tim. So like I said, a little old there. They kind of jump a little bit. But low on fuel, it looks like you're gonna go one of two ways. And this will tell you real quick, a bimetallic, high is 10 ohms and low is 73 ohms, where a metallic is low is 15 ohms and a high is 160 ohms. So they're inverted from each other. So gives you a little bit of reference, but so we actually use a resistor block and we can go in and actually see is the gauge sitting at different points. Also, we have a midpoint on several of them. So depending on the manufacturer, like International Harvester here, General Motors, Toyota, Volkswagen, even down to tractors, John Deere. So I mean, there's all kinds of, but again, kind of a quick sheet. Again, something I bought obviously a number of years ago and still use it today. So that's, you know, again, so we're not really testing the gauge, we're inducing a resistance and seeing how the gauge operates.
Sir Brian,
Yes.
the sensor is set to recognize the reserve capacity in the fuel tank, right? It's not set as really empty, because I understand there's some certain reserve in the fuel tank and that really goes empty.
Yeah, so the reserve capacity when it reads empty varies by manufacturer. And you really shouldn't rely on that, but yeah, empty doesn't necessarily mean that there's nothing in the tank by the time the gauge gets empty, because it moves with a float. So this float rides on top of the fuel. Here we can see our rheostat, and here's the two wires coming out of it. So it's gonna ride. So it can only, that's why it may stay full for a long time and then drop very quickly and then stay empty for a long time. So it kind of depends on how they've designed the tank and how they've designed the float in that vehicle. But on most vehicles, simply just, you know, checking, you know, ground, does it go all the way high? Open, does it go all the way low? If it does that, then we put a new send unit in it. We do not see a lot of gauge calibration issues. It does happen sometimes. The other thing they do in instrument clusters is they use a voltage regulator. So they actually lower the voltage from system voltage down. And if that voltage regulator is bad in the dash, it can cause the gauges to read high. And
can you touch on that real quick a little more, Brian? I don't get what the voltage regulator does in the instrument cluster there. What's its purpose again?
Okay, what its purpose is to give a steady voltage, because we really don't want our gauge to read differently when the car is off than when it's running, or if I accelerate and go from, you know, 13.5 to 14.5, we don't want to see all the gauges necessarily move as we accelerate and decelerate, which was a problem in the past. The other thing is I don't need to necessarily run 12 volts down to my send units, whether it's for temperature, oil, or fuel level. So some manufacturers limited that voltage to 5 volts, some limited it to 9 volts. So some manufacturers put a voltage regulator in there so that it would now have a steady, say, 9 volts. And so that way the gauge would stay accurate regardless of what the battery voltage is doing between 12 volts and 14.5 volts. The gauges wouldn't all be jumping. And that also led to a little more accuracy of the gauges. So they would use a voltage regulator to drop the voltage down. Not all manufacturers did this, but many did.
Okay.
And we saw that up into the 90s. More common on newer vehicles, but it goes back to the 60s. I mean, so it's not a, but yeah, there was a basically just you know, voltage regulator built onto it that dropped the voltage going to the gauges so that it was constant. It was no longer battery voltage.
And then here's kind of, I think, a dumb question, but so in the case of the fuel lever sensor, you got 2 wires going to it, a power and a ground, obviously. And then in my example of the oil pressure sending, I have 1 wire that goes to it, and the sending unit itself is grounded to the block.
Right.
What's the reason for that? Why you know, why the difference, or why?
Well,
is there a reason? Like I said, it might be a dumb question. Is it just
no,
split
not
hairs?
a dumb question at all, because it's the same circuit. And one is we're running wires, we're running both wires to the send unit, and the other one is we're running one wire to a send unit and relying on the threads for the other connection. And the reality is there's a lot of vehicles, especially going back to the 60s when we used metal fuel tanks, that only had one wire going to the send unit for the fuel.
They did. Okay. Okay.
Yeah, see, newer vehicles, because we have plastic tanks, now I can no longer do that. Also, there's obviously certain issues when we're relying on a connection through a tank or through a block. So we will see some stuff with two wires going to it because they want that redundancy. But the reason why they go one wire is it's cheaper, right?
Yeah, that's kind of my point.
How
Like,
much
why
wire
wouldn't
we
you?
saved on 1 million vehicles?
Yeah, if I can run one wire all the way back to the gas tank, why wouldn't I do that if it's cheaper? You know, so there's just a question of, well, if you're using a plastic gas tank, that's you got to. Okay, got it.
Yeah, so some of it is accuracy, some of it is, I mean, a lot of times in oil is just on-off pressure switch. Where a gauge, I want a little more accuracy, so I may see two wires go into a gauge with one wire going to that. That gets into an engineering decision. But you know, the end nut is that you know, all newer vehicles for the last 30 years, for the most part, have had plastic gas tanks. You know, certainly a majority of them. But there is quite a few that did use a single wire sensor with metal gas tanks. If I get in the Wayback Machine, go back to the 60s and 70s and into the 80s. But some of it, I think, was customers wanted more accuracy also. You know, they're tired of what in the old, I remember my 73 Delta 88. If you, when you got to half a tank, when you accelerated, the tank went to zero. And when you were stopping, it'd go to full. You know,
Just from the sloshing in there.
Just from the sloshing in there.
Yeah.
And now, how many of you have a trip computer on your car that gives you distance to empty? Right? So if I want distance to empty and I don't want this, I need to put some baffling in the tank and I need a more accurate send unit.
So this would explain something, I think. This is cool. So I rewired the truck last year. My fuel gauge always would never go higher than 3/4 of a tank. It's full. I know I filled it. I could see gas spilling out the top. 3/4 was the best I could get. With the all new wiring, I go all the way to full now. So that was a resistance thing. The old wire had higher resistance. I'm trying to talk this through. Had higher resistance, hence showing, you know, a lower. Okay, so I thought that.
Absolutely, yeah. Your old wire or connection that some of the old wires connected, one of the two or connectors, had higher resistance, and that's why your gauge was only going to 3/4.
That's cool, man.
Yeah. See, when you figure out how things work, all these mysteries start making sense. No, that's real cool. So a little two-wire sensor review. All two-wire sensors work by changing the resistance in the circuit they're installed in.
I'm gonna go true.
True.
Yeah, really true. I mean, you can kind of waffle a little bit on permanent magnet, but this really gets the concept. I'm really looking for a true there. So 3-wire sensors. So here's just a few 3-wire sensors. I can have a camshaft position sensor. I can also have a crankshaft position sensor, just 3-way. I mean, we do 3-wire sensors, all that stuff. EGR position, throttle position, manifold absolute pressure, mass airflow. So you guys may have heard of some of these, like a mass airflow sensor or throttle position sensor. So these are all 3-wire sensors. We're going to see that they share some things in common. We have some rules that we can apply to 3-wire sensors instantly by looking at them. And then I'm going to look at the different types of signals that are generated by them. So the first one we're going to look at is a potentiometer, which is my TPS sensor or EGR sensor, because it's the easiest way of explaining how the circuit works. And something we can visualize a little better, which is why I use it. So the most common type of position sensor contains a mechanical arm that is attached to a moving component, throttle plate, accelerator pedal, airflow door, lower control arm, upper control arm, air door in your dash, any number of things, EGR shaft, position shaft, which causes it to slide across a fixed resistor within the sensor. So what this looks like electrically is I have a ground, I have a power, and this isn't drawn quite right. The 5-volt reference should be showing here. There is a resistor after the 5-volt reference, not the 5-volt reference during or before a resistor. Because we're dropping down to 5 volts. So 5 volts is our VREF. We're dropping it down to that, and that drop down, or that transformer that we do that with, already provides the protection. So we really only have one resistor in the circuit. In this case, it's a fixed resistor. So I have 5 volts. It's going to come out, go through this resistor, and back to ground. So I always have 5 volts here. I'm not using any 5 volts on this internal resistor. I should probably go in and try to block this out and modify this slide. This is a factory schematic, to give you an idea. But I have 5 volts coming out. This resistor always uses 5 volts. So if I measure between A and B, put my positive meter lead to A, negative meter lead to B, I should always see 5 volts there, no matter what my throttle position is, whether it's at idle, whether it's to the floor, it's not going to change. What is going to change is C, and that's my throttle position sensor signal. And based on position, this is going to move up and down on this resistor. And what it's acting like back in the computer is a digital multimeter. So pretend this is a lead for a digital multimeter, and I'm measuring the voltage available here compared to the voltage available here, here, or here. So if I start with 5 volts, and at the end I have 0 volts, I have to drop that voltage a little at a time going through here. So if I measure at the top, I probably got 4 volts. Here I'd have 3 volts, 2, 1, and then down to 0. So right in the middle, I'd see 2.5 volts. So depending on what I'm measuring how much this resistor is using. And so this arm is what's attached to my throttle shaft. It's attached to an air door. It's attached to anything I want to measure. I can put it on a shaft in the case of EGR, which just goes up and down in a linear fashion. I can measure it and see how far I'm lifting it up or putting it back down. So anything that I want to measure very precisely, a position of either rotationally or on a vertical up and down, I use a potentiometer for. And these have a power, a ground, and a signal return. So if I'm testing this, I can look at C to see if my signal return is what it should be. I could measure between A and B and make sure I have my 5 volts there. If I don't have 5 volts, then I got to figure out, do I have a bad connection or wire on the power, or a bad problem on the ground because someone's stealing our voltage. So it's a series circuit from here through here. It is measured in parallel by my throttle position sensor signal. There is no current that goes through here. There is a huge mega ohm resistor in there that prevents current from flowing through there. So this is not part of my circuit from a voltage drop standpoint. This resistor uses all my voltage. All I'm doing is measuring the different parts of the resistor to see how much of the voltage was used at any given point. And since that arm is attached to something that's rotating, then it sends a signal back to the computer saying, oh, 5 volts, you're all the way, you got your foot to the floor. Oh, 0.5 volt, oh, you got your foot off the gas. So we're just using that voltage to tell the computer what position we've moved that arm on as it slides across this resistor. So because of this, these will wear out because they're what? They're constantly rubbing. And so they will get bad spots in them that causes problems. More common on older ones than newer ones that make them a lot better now. So here it is on a vehicle. So here is a throttle position sensor, 3 wires. I have an orange, a black and green, and a white and purple. This is my MAP sensor, manifold absolute pressure sensor, that we'll talk about shortly. But I want you to notice a similarity while we're here. You notice I have a green and black, a green and black, a purple and white, a purple and white. But this one has an orange in the middle. This one looks like a green and orange in the middle. So both of these sensors are sharing the power, the 5-volt VREF, and they're both sharing the ground. The only thing different between them is the voltage coming back to the computer, the signal return. So even though they work very differently inside, once we get outside of the little magic plastic thing here, they're identical. Power, ground, signal return. All 3 wire sensors are going to give us a power, a ground, and a signal return. I don't care if I'm working on a climate control system, a suspension system, braking system, engine system, transmission system, 3-wire sensor, power, ground, signal return. Now the signal is going to look different. It's going to have different ranges, but we still have power, ground, signal return. So when we see a 3-wire sensor, we should understand that that's what we're looking for. We're going to have a voltage reference, we're going to have a ground, and we're going to have a wire that sends back a signal to the computer. So if I want to test this, I could use a voltmeter and measure, am I dropping all my 5 volts across here? And what's my voltage here when the throttle's closed? And I can open the throttle a little bit and watch the voltage change. But it's possible, because my meter only updates about every 200 milliseconds, that I can have something happen between those events. So what I really want to do is I want to use a lab scope. So what I have here is I have a lab scope set up. I'm between 0 and 5 seconds. And I'm between 0 and 5 volts. And what we've done is we've slowly moved the throttle. And we're going, you can see here, I'm about 3/4 of a second, and I'm done at about 4 1/4 seconds. So I use about 3.5 seconds here. So I want to go slow. Because I'm going slow, I need to do this with the engine off, or I would overrev the engine doing this. So we do this with the engine off. And we're going to walk the throttle from closed to all the way open and back to close. And we should look pretty nice and even. Here, the initial snap was a little quick and then slowed down for the rest of the movement. But we can see here where it went through nice and even. And this would be a known good pattern. I'm getting up to about 4.5 volts, and I'm down about 0.5 volt. So that's giving me a good range. Sensors use what we call a 90-10 rule. Means they normally don't use the lower 10% of their voltage or the upper 90% of their voltage. So I shouldn't see 0 volts and I shouldn't see 5 volts when I do this, because the computer uses that for fault detection. So if this is stuck at 5 volts or it's stuck at 0 volts, that tells the computer there's a problem with the sensor. Either something is shorted or something's unplugged or something's missing. For example, if the ground wire was broken, we would see 5 volts all the time. If the power wire was broken, we would see 0 volts all the time. So that's what the computer uses for fault detection. So the operating range of the sensor is not going to be 0. It's not going to be 5. It's going to be in the middle. And that's what we call our 90-10 rule. And that's what sets codes. So what sets codes for these sensors is when it violates the 90-10 rule. Things will set a code. So here's a malfunctioning TPS. Again, keep in mind, we do this very slow because I want to find more problems doing it slow. And now I'm moving the throttle and the sensor drops out. Boom, it comes back up. I come all the way up here. I come back down, and when I get to here, it drops out again, and then it's back down here. So this is a worn out throttle position sensor. It has a bad spot right as you first give it gas. Well, think about it. Where does your foot spend most of the time? Just a little bit in on the throttle, and it's doing a lot of this. So eventually it can wear out the throttle position sensor. And so when it does, the symptom on this car, when we drove it, was if you put your foot down really fast, the car took off and ran great. But if you slowly accelerated, it would start going and then kind of kick and then whip you back in your seat. Because think about what's happening. We're coming along, the computer knows that we're accelerating, and then, oh, we took our foot off the gas. Then we slammed our foot on our gas really, really quick. So we went from slowly giving it more gas to not giving it any more gas to giving it a whole bunch of gas. And that's what caused that jerk on acceleration, because the computer is responding to the sensor. And this is one of the reasons, and this is an old scope, by the way. It's a big old stationary one. But this shows you why we look at things on a scope. It's because we can see these things happening. And again, we know it should be the same as I go up, as I do when I go down. It is the same. And it's a bad sensor, because a bad sensor is the only thing that's going to cause that. A wiring or connection issue isn't going to cause that. A wiring or connection issue is far more random. And here we can see it dropped out almost exactly the same spot, opening the throttle as it did closing the throttle. The only thing that can do that's a bad sensor. So the TPS return wire most clearly resembles what meter function?
One.
One, absolutely, voltmeter. So here's an EGR position sensor. So this is an exhaust gas recirculation valve, one of the emission control pieces on the vehicle. The computer must be able to verify that the EGR valve is moving correctly when commanded by the module. So the module is going to allow vacuum to come into a diaphragm. The diaphragm lifts up. As it lifts up the shaft in the middle, allowing exhaust gas to recirculate. And there's a plunger built into the sensor that goes on the top of that. And as that diaphragm goes up, the plunger moves where the plunger is a resistor. So it's going up right through where the sensor is there. And we're taking a look and seeing how does it change. And that's what gives the feedback to the computer. So this, again, 3 wires, 5-volt VREF. I'm going to go between 0.5 volt and 4.5 volts. From there, I look for manufacturer specific specifications on what it should be. But that's the normal range of it, and that's what we're going to get. So power, ground, signal return. Very different name, right? EGR position sensor. That sounds completely different than a throttle position sensor, other than the word position. And a lot of times these are just called an EGR sensor. But seeing that it's 3 wires, yeah, okay, I know what I need to do here. I know what it's measuring. I know how it works. It's a position sensor. It has a power, has a vehicle reference point, power, voltage reference sensor with power, or ground, and a signal return. I just need to figure out which wire is which so I can test it. Now, on pre-OBD2 vehicles, there were some Bosch systems that used a 3-wire switch on the throttle position sensor instead of a potentiometer. And so we saw these on European vehicles and also Asian vehicles using a Bosch LJET system. And so these had 3 wires, but here we can see a couple of different ways. One was we had 12 volts in the middle, and we would either send a signal to wide open throttle or idle. Here we'd have 12 or 5 volts and ground, and we would change the signal. So you quickly know, when you have one of these, because you go from nothing to everything, there is no gradual movement of voltage. So these Bosch systems only need to know if I was at idle or my foot was to the floor. It didn't care about in between. And I only mention these, again, we haven't used these in 27 years now, probably. I only mention these because I do know people run into older cars, and you just need to be aware these are out there. So if you have something that doesn't work at all, like what a throttle position sensor should, and it's mounted on the throttle shaft, and you're working on something old, you should be asking yourself, wait a minute, does this thing use a set of switches? Let me go get the manual. Let me go look up and see what they're doing here before I start putting parts in. And that's really the purpose of it. I don't, it's, my whole expectation here is that you know that they exist and they're only used on throttles. And that's really the limit of it. We can see here modern throttle position sensors down here where we have a ground, a VREF, and a signal return. And this one does show that internal resistor and signal return, so a very large resistor. So again, just so you know they're out there. So some electrical assemblies mounted on the throttle shaft are actually a pair of switches and not a 3-wire sensor. Is that true or false?
False.
True.
It's true.
True. I just discussed it right here.
Okay, I didn't fully understand.
Not a problem. That's why I asked the question. A lot of times you guys think I just ask these redundant questions like he just covered that. Well, covering it and covering it clearly are two different things. So some manufacturers, instead of having this throttle position sensor where this needle moves up and down with the throttle shaft movement, put a set of switches in. It was still a 3-wire connector, but you'd have a switch that closed at idle. Then you'd have open, and then another switch at the top, and it would close when you got all the way to wide open throttle or your foot on the floor. So the computer only needed to know, is our foot on the floor or is our foot at idle? It didn't care about anything in between. We're at idle, our foot's to the floor. That's all it cared about. So these are the two wiring configurations that we used for that, either a center ground or a center voltage signal, but two switches. And so here we're switching this to ground because we're dropping our voltage through the resistor here, which makes the circuit between ground, a resistor, and back to voltage supply. And so here we put the resistor here, so we would just collapse the circuit. Both of these would be grounded. And see the voltage come one way or the other. So a couple of different ways of doing it, whether we want to switch power or ground. But we use these switches, and like I said, we used them up into the 90s is another reason why I cover it. So Mercedes used it till 96, I think. 95, 96 was the end of CIS for Mercedes. Several Asian manufacturers also used it in the 90s. So it wasn't, domestic vehicles never used this. But some of the Bosch systems that were used for both European vehicles, and then were also used by Asian manufacturers like Toyota, Nissan, and so on.
Okay.
Use these systems. So the big thing is just to make you aware that they're out there. Not so much that you need to be an expert on them, but if I'm going to test a TPS and things don't make sense, wait a minute, I should have, a reference here, and I should have a signaling change, and it's not working how I think it should, and I'm getting confused. Go get the manual and see if this is what you have. So that's really the only lesson here, to let you know, hey, there is some stuff out there that we did in the past. There's some stuff out there that doesn't work the way stuff does today. Just like Tim brought up the sensors, and I'm going that, yeah, we did have some of those that worked opposite, and you had high resistance for low and low resistance for high. I'm sorry, backwards of it. And yet those are all, 72 and older. I mean, so why would we put it in a college textbook when no one's probably working on those? To me, that's ancient. As opposed to drivability, there's still a lot of people out there, especially when you look at, these are like anything from, a Nissan, 280Z to a Mercedes, Lotus, Rolls, Porsche. A lot of cars out there did this, and these are cars that have enough value that they're still out there today. And that's kind of one reason why I bring this up.
Okay, I heard you say that. I just didn't. I get the question. It was confusing to me, but now I got you. I have a question. Okay, some electrical assembly is mounted on the throttle shaft.
And it should be switches.
Yeah.
Yeah.
Okay, I got you. True.
Yeah, true. So again, this is really the extent of the knowledge that I'm trying to empower you guys with here, is that it is true that, well, when things don't follow our rules, because manufacturers are constantly doing weird things. We have some rules that I try to impart. Just like 3-wire sensors should be power ground signal return.
Okay,
On the other hand, if I connect something and it's not following those rules, now I need to do research.
Can I ask a quick question?
Yeah.
Okay, 2 slides before this one is on with the EGR. They have the EGR. Okay.
Yep.
Position sensor. Now, is that on every vehicle?
No.
Or something. Okay, I didn't think so.
No, it's only on some vehicles that use EGR. So not all vehicles use exhaust gas recirculation, and not all vehicles with exhaust gas circulation use a position sensor.
Okay.
There are some that do. This happens to be Ford. GM does on some, Honda does on some, and so on. So there's quite a few manufacturers that do. It's a common sensor. And that's why I covered it by name. But electrically, it works the same as our throttle position sensor. There's no difference. I'm going to test it the same way. The difference is, how do I make the EGR move up and down as opposed to how do I make the throttle rotate open and closed?
Okay. Thank you.
You bet.
Sir Brian,
Yes.
the two switches are only on the throttle, right? Not on other sensors.
I'm sorry, what?
The two switches, that's only for the throttle, not
Yes.
on other sensors.
Yeah, only used on the throttle.
Okay, thank you.
So pressure sensors. So there's two types of pressure. There is atmospheric pressure. For example, in the room I'm sitting in, there's approximately 14.7 PSI currently. We also sometimes call that our barometric pressure, right? And we know that, you know, you hear on the weather, we have a high pressure area, so it's dry and hot, and a low pressure area, kind of cold, rainy. So we do have atmospheric pressure, and that atmospheric pressure is going to change with altitude. You know, you hear them say, hey, the air is thinner at Mile High Stadium. So they might be able to make the field goal easier than they would in San Diego because the air is thinner, less pressure. We also have what's called gauge pressure. So gauge pressure is going to be 0 PSI here, and it's going to be 0 PSI in Denver. Gauge pressure starts at 0 and measures the difference between whatever pressure we're reading in our atmospheric pressure. So gauge pressure is really a difference. Absolute pressure includes the pressure of the atmosphere. So two different pressure scales, and cars use both and don't always tell you which one they're using. So sometimes I have to take a number and add back in this 14.7 or subtract this 14.7 to make things make sense. Pressure sensors monitor the pressure differential between atmospheric pressure and pressure within a component or system. So we do have those. So if I'm reading gauge pressure, for example, fuel, and I say that we have 70 PSI of fuel, I might be reading just gauge pressure. So that's 70 PSI on top of our atmospheric pressure. Or I might use a fuel pressure sensor that is telling me 70 PSI that's in real pressure, absolute pressure, and it's actually only 55 PSI in the fuel rail. So it's important to know which pressure scale we're using with these sensors. How the sensor works electrically is the same. It's simply a scaling issue for us, and that's why I bring that up. So pressure sensors also monitor barometric pressure, atmosphere, or baro as we call it, because I have to know whether I'm in Denver or whether I'm in San Diego in order to calculate the right amount of fuel going in the engine. So there's two different ways that we have of measuring the air coming in the engine. And we're going to discuss both of the sensors used in this presentation. One of them is the manifold absolute pressure sensor. And we're using pressure to infer the weight of the air, and therefore we can put in the correct amount of fuel. Or I can use a mass airflow sensor where I'm actually measuring the grams of air coming in or the weight of the air coming in to the engine so I can give it the correct amount of fuel. The issue we have is on a modern engine where it's fuel injected, we know the weight of the fuel. I know that at this pressure, spraying fuel through this size orifice for this amount of time will deliver a certain weight of fuel into the engine.
So this works kind of like a pitot-meter on a plane? You know, the little pitot-meter
yeah,
that's up the side of the plane that measures?
Measures the altitude, right.
Okay.
Yeah, very similar. So that's our baro, except for we don't go to 30,000 feet. So yeah, exactly. So in the old days, baro sensors would only calibrate when you turn the car off. So you might take off from here and go skiing up at Big Bear, and halfway up the hill, the car barely runs. And man, you know, something's wrong. I'm going to pull over, pop the hood and look. Not that I know what I'm looking at. So we pull over, shut the car off, pop the hood, look around, poke around, not see anything. Then fire the car back up, and then it would run great again. Well, because it recalibrated for that higher altitude. Today, cars are able to calibrate while they're running. We build things into them to allow them to calibrate while running. So
So-
yeah, exactly. We need to know the altitude so we know how to mix the fuel.
So this will be related to the efficiency of the use of fuel because it measures the air that comes in that mixes with the oil to run the engine, right, Sir Brian?
Yeah, so we need to know the weight of the fuel since we know, I mean, we need to know the weight of the air since we know the weight of the fuel. And I want to match those up to close to what we call a stoichiometric mixture, which for gasoline powered engines is 14.7 pounds of air for every pound of fuel. And since I know the weight of the fuel, I have to try to measure the weight of the air. So whether I'm using the engine coolant temperature sensor and air temperature sensor, because weight of the air changes with temperature, just like it does with altitude. And then I need to measure the pressure of the air or the volume of air coming in the engine. So it's all about, so a lot of these sensors are about measuring the air. You know, we think of our throttle position sensor as a sensor that makes us go fast. The throttle position sensor actually just is really a request sensor. It's letting the computer know what the driver's intent is. It's telling the computer, I want to go fast or I don't want to go fast. There's not, you know, the sensor itself, even though I'm opening up the throttle plate and I'm putting air in, if I don't give it any fuel, we're not going anywhere. So that lets the computer know, hey, we need to get fuel because we just put a whole lot more air in this engine. And on newer vehicles where the computer controls the throttle, and now we have an accelerator pedal position sensor, which is truly telling the computer what the driver's intent is. What do I want to do? But what I want to do is also dependent on these other sensors to make sure things happen correctly. And one of them is pressure sensors. So when we look at the pressure sensors, these are 3-wire sensors. A 3-wire sensor has a reference voltage from the PCM, a ground, and a signal return wire. Common sensors used today are a manifold absolute pressure sensor, or MAP as we call it, a fuel tank pressure sensor. So many manufacturers use a very, very sensitive sensor for measuring pressure changes in the fuel tank to detect a leak or if you left the gas cap off and turn the check engine light on. Our barometric pressure sensor, or baro sensor, a delta pressure feedback sensor for the EGR system to measure EGR flow. And we basically put 2 pressure sensors on either side of an orifice. And if there's a restriction in flow, we know there's a differential in pressure, just like there is in electricity, right? Electricity is pressure. So here we're going to use a set of gauges for air pressure difference. Fuel pressure sensor. And we see this a lot on modern vehicles where we have direct injection. Previous vehicles, some cars had a fuel pressure sensor, but many didn't. Once we go to direct injection, they all have to have a fuel pressure sensor. And so this is just some of the examples of different types of pressure sensors. And even though they'll work differently internally, what they're doing is the same. They're dividing that VREF, that 5 volts that's applied to it. And we're going to send back a return signal based on how much pressure we have. So here is a MAP sensor. We have a vacuum hose connecting to it. And there's a 3-wire connector here. And the 3-wire connector contains my power, my ground, and my signal return. So I could spend the next hour talking about the Wheatstone Bridge and the other ways that the internal of a MAP sensor works and really, really make your heads hurt. But the reality is, I don't care. I'm not going to open it up. I'm not going to fix it. What I need to know is right here. I have a MAP sensor that measures changes in vacuum. Vacuum is just pressure that is below atmospheric. And I have a power wire, a ground wire, and a signal return wire. I know that I need to use all of my 5 volts between A and C, and I'm going to get a signal that's sent back to the computer on B. What's that signal supposed to be? It varies slightly by manufacturer, so I would want to look at the manufacturer specifications for this vehicle. Normally, we're pretty close to 5 volts with the key off. With the key on, engine off. And I'm going to be down somewhere between 0.8 and 1.5 volts with the engine running, depending on manufacturer. And that's a big difference on manufacturers. So where some manufacturers want 1.2 volts, 1.5 volts, Honda says anything over a volt is a major problem. So it really does vary a lot. So we do need to look up specifications on what that manufacturer wants for signal return voltage. But if my signal return voltage is not correct, I need to check and make sure I have all my 5 volts between A and C. If I do, I double check that what I have at B is what I have here at F15. If it is and it's not correct, I either need a new sensor or the vacuum hose here is bad or has a hole in it or a split in it. So I'm not opening it up to test it. So going in and talking about something that's fairly complicated and how it works inside, basically there's a pressure diaphragm in there, and as it moves, there's 4 resistors on it, and it changes the overall resistance, and it's a parallel circuit, so it drops the voltage and so on. And that's a way overly simplistic analysis. But again, all I need to know is as pressure changes, my signal at B is going to change. Since all my test points are outside of my map sensor, Tinkerbell, who I got with me today, I got Tink with me today, she could have filled it with pixie dust. It doesn't matter. So whether it's got pixie dust inside or whether it's got a Wheatstone bridge inside makes no difference on the signal that it should be putting out. So I'm strictly comparing, is the signal that it's putting out consistent with the vacuum supply that it's getting or lack of vacuum that's getting. So I can use a handheld vacuum pump and manually apply vacuum and test my signal. The quickest test we do is just key on engine off without the engine running, do an atmospheric voltage check. Is that in specifications? And then from there, I'm testing the circuit. So what happens inside really doesn't matter. And that's, the only reason why I go into as much detail on the TPS is because it explains how we divide the voltage on the circuit. The other ways we do it really is unimportant when it comes to fixing cars. It's kind of nice to know some people really geek out on it. Some people really enjoy learning about it. But when it comes down to a fixing car standpoint, it doesn't help us. So both the TPS and map sensor circuits work the same way electrically from outside of the sensor to the PCM. Is that true or false?
True.
Mm-hmm. Absolutely, it's true. And that's really what I want to emphasize. A 3-wire sensor is a 3-wire sensor is a 3-wire sensor. It has to drop all of the applied voltage that's supposed to be sent to it. If it doesn't have the correct voltage to it, it's not going to give me the correct signal back. And then once I verify it has the correct voltage going to it, it better have the correct signal coming back. If it doesn't, it's a bad sensor or it's getting a bad, it's not getting the right amount of vacuum. In other words, my engine's running, it should read under a volt, but yet the vacuum hose has a hole in it. So it's not going to see all the vacuum, things like that. So unless there's a mechanical on the input sensor side, very straightforward. So Hall effect sensors are used where accuracy and fast response are important. So one of the advantages that the Hall has is that it doesn't need a certain amount of speed of interruption. So if it is going that fast or it's going this fast, it's going to have the same level of accuracy. So very, very accurate sensors, a little more to produce, which is why we don't necessarily see them in some places. We see permanent magnet sensors. The other advantage we have is because it sees from the first movement, we don't have that loss of visibility that we do with permanent magnets. So permanent magnet doesn't see the initial rotation of something. So commonly with ABS sensors that use permanent magnet, we don't see under 3 miles an hour. Where with a Hall, I can see all the way down to 0 miles an hour. I can see if you just roll back a little bit or roll forward a little bit.
What are you seeing? It's on performance cars or something? Or
they're used really on all cars in one form or another. We see some manufacturers use a permanent magnet for a crank sensor and then a Hall sensor for a camshaft sensor. We see some manufacturers use Hall both places. We have some modified Halls. that we use for some wheel speed sensors now that I demonstrate on the lab video that I got coming up. So these are more expensive, but they're more accurate. So if the engineers don't think they need the accuracy of a hull, they're going to throw a permanent magnet in if it's a rotating component. On the other hand, if they want that accuracy, or if they can't use a permanent magnet, but they need to see movement, not just position, they're gonna use a hull. So we use hull sensors not only for things like camshaft sensors or transmission speed or vehicle speed, same place we use permanent magnet, but I can also use a hull sensor for measuring where my window's at. Is it halfway up, all the way up? How fast is it going? I can use it on my brake pedal. Not only did I apply the brakes like an open close brake light switch, how far did I apply the brakes? In other words, how far did I move? And how quickly did I move there? In other words, did my foot slowly kind of go down to the floor because I'm leisurely stopping coming to a light? Or did I just do a panic stop where I applied a lot of force very quickly? So with a hull, by not only looking at the speed of interruption, but also by changing the size of the holes that I'm interrupting, changing the pattern, I can tell exact position of things, which I'm going to show you coming up. So it's really, and I can figure out that position very, very quickly. So Porsche, for example, back in 2010, when they first did the Panamera and they were using start stop on the Porsche with a stick shift, they used 3 Hall sensors built into one housing for the crankshaft sensor. So it actually had 3 of them, and the pattern would be different whether the engine was rotating one way or the other. So they could tell if the car was rolling back and the engine was starting to rotate in reverse, so they could apply the brakes to keep the car from rolling back. So that way, when they ran the starter and the engine wasn't going the opposite direction and some other things. So they were able to see exactly not only the position of the engine, where it was, how to start the engine quickly and seamlessly, but also tell if it was rotating the opposite direction. But they used 3 Hall switches all in one housing for a crank sensor to do that. So very, very high tech. So that would be your luxury performance vehicle. But again, at $100,000+, you can afford to put that technology in.
So is this kind of synonymous with an actuator kind of? I mean,
no, not at all. This is only a sensor, not an actuator.
okay.
An actuator is something a computer can send an electrical signal to make something happen.
Okay.
So even though the computer is supplying power here with power and ground, we still have a signal return. So we're going to we have power, ground, signal return, just like every other 3-wire sensors. The difference is the signal return looks different because it's a Hall.
Okay. It's just a sensor then. Okay.
It is totally a sensor. Absolutely. So, oops, I'll go through. So a powerful magnet, as the magnet passes over a dense portion of the trigger wheel, the 5 volts is pulled to ground when the about 0.3 volts. And the reason why we're not going all the way to ground is A, it's through a transistor, and B, it allows us for fault recognition. I remember going back to our 90-10 theory. When the magnet passes over a notch in the trigger wheel, the 5 volts is restored. So Hall effect sensors can be used for crank, cam, VSS, ABS, brake pedal position, clutch pedal position, power windows, sunroof, just to name a few. So we use these for all kinds of stuff. Hall sensors do a much better job of detecting movement at low speed when compared to permanent magnet sensors. So here is a vehicle right here, and it actually has 2 sensors, a crankshaft sensor and a camshaft sensor. I can see they have 3 wires going to them. So a 3-wire position sensor is going to be a Hall. 3-wire sensor should have a power, ground, and a signal return. And if I look here, I've got ignition feed. So there's power. Oh, ignition feed, there's power. I've got ground, which is my reference low. So reference low is another name for ground. We talked about that a little bit in wiring schematics. GM likes to call it reference low, but that means ground. And then I have what? Cam sensor signal input. So there's my signal return and my crank sensor signal input. So in this case, I would want to test that the A's looking for the correct signal. If I didn't get the correct signal, then I would need to verify that I had power and ground going to the sensor. If I have power and ground going to the sensor and no sensor signal, I've got two possibilities, either a bad sensor, most likely, or whatever it's measuring is not moving or no longer attached. And occasionally we'll see stuff come apart inside an engine or something weird happening. But still, the first test is you're going to put a sensor on it and look around and see if there's anything broken inside or see if the new sensor has the same problem. Because sometimes we do see mechanical issues affect that. So here is my sensor right here. And hey, I can see everybody. I'm getting 5 volts. When we come through and interrupt it, I'm getting 0 volts. And I get a square wave or digital signal. Square wave, digital mean the same thing. And this is very precise. And if you notice, I can have a pattern here that repeats. So it allows the computer to know, based on what it sees and what comes next, exactly where I am in the cycle. So it allows me a lot of detail. And now I can figure out where I am without going all the way around. I can find out very quickly. So early systems might only tell me, hey, it goes around once. Hey, you went around. Hey, you went around. Hey, you went around. Newer vehicles, I actually want to know much more precisely all the way that 360 degrees where we are, so I can start the car faster. Because the quicker I can start the car, that lowers emissions. One of the times your car pollutes the most is actually starting when you first start it. And so they want to lower those emissions by having that car not have to crank over once or twice or longer before it finally starts. So here again, back to a scope. I'm looking at a car that has both a crank sensor and a camshaft sensor that are both Hall effect sensors. So here's my cam sensor, and my engine goes around, my crankshaft went around once, twice. My camshaft went around once. And what this allows me to do is the manufacturer actually tells me where this is supposed to line up with this. And in this case, this is supposed to be exactly centered. And I could bring over cursors, which are lines. I could put them on top and I could actually see that, yes, I'm centered. If I wasn't centered, that would tell me that my timing chain stretch, guide stretch, things like that. So we do get codes on cars today saying that there's a problem with my camshaft sensor, crankshaft sensor, or with the timing between the two. And being able to test this with a scope is a huge time saver. Some of these cars are like 18 hours to take apart and put back together just to look at it. No one's going to pay that. It's not practical. So we have to be able to test these things using these sensors and rely on what these sensors tell us. So you can see here, square wave signal. We know square wave is a digital signal. And again, I can use the signals to compare the position of my camshaft sensor up top in white to my crankshaft sensor in yellow at the bottom. So just as we did when I had a permanent magnet sensor and a Hall, when I looked at permanent magnets, I can do that comparison. I can do it here where I have both Hall effects. The Halls make it a little easier to see because of their shape.
Why is there a missing signal in the middle?
Why is what in the middle?
Like there's a missing signal on top of.
Oh, you mean right here?
Inversion.
Yeah.
Right here, you mean, Cynthia?
Yes.
Okay, so it's not missing. This went around twice. This only went around once.
Once. So it's like the rotation.
Right? And this leads me into our next module, which is engines. And we're going to find out that my camshaft only goes around once, even though my crankshaft goes around twice. So I kind of introduced this here because this leads into what we're going to be covering in the next module. So here is the camshaft sensor. This right here happens to be Ford. And they call it a synchronizer, is their cool little name for it. But what does it have? 1, 2, 3 wires. Gee, it's a sensor with 3 wires. Any bets we got a power, a ground, and a signal return?
Yes.
So you see how that little bit of knowledge really makes it a lot easier to diagnose a whole bunch of things. So Hall sensors generate what type of electrical signal?
Four.
And
Four, absolutely.
Both 2 and 3.
digital
Yeah,
square.
exactly. A digital square wave signal. So number 4. So here's a quick sensor comparison. Here's my variable reluctance or permanent magnet sensor, and it creates an analog signal, and this is going to change both in frequency and amplitude with the speed of rotation. On a Hall sensor, 3-wire, my amplitude never changes, but my frequency will as we increase speed. So in other words, obviously, if I spin this faster, I get more square waves in the same amount of time than if I'm spinning it slow. But the height of my square wave never changes. Where with the variable reluctance sensor, the height of my waveform changes directly based on how fast we're spinning that. And so based on how fast I spin it, I can have almost no up to huge, and then no, and then all the way up really big, and then back down really small. And it's small because this is an analog signal going into a computer. If it doesn't have enough amplitude, the computer will not see it. It will not switch the analog to digital converter inside the computer, and the computer thinks nothing happened. As opposed to our Hall sensor or Hall switch, as it goes very slow, it's still going between the low and the high. So the computer sees
Number
everything.
one for come here, but she cannot.
Why?
The variance.
Working, and
on
they
the
just
first one.
What's that, Ashley?
I was just saying, so there's a variance in the first one, the variable reluctance sensor. It it fluctuates.
Right. That AC waveform is going to fluctuate in both amplitude and frequency, where the Hall effect only frequency changes, your amplitude never changes.
So that's why it only needs the 2 wires.
Yeah, well, it makes its own voltage is why it only needs 2 wires. So there's no voltage applied to it. It generates its own voltage.
Okay. That makes sense. Thanks.
Yeah. You bet. So mass airflow sensor, the most common type of mass airflow sensor used today is what we call a hot wire mass airflow sensor. There are other kinds of mass airflow sensors, Karman Vortex to name one, which use sound. And there's airflow doors. There's all kinds of different things that we saw on pre-OBD2 vehicles. We're not going to go there. Like Karman Vortex sensors are long since obsolete and were never widely used. Bosch L-Jet used an airflow door, both on Nissan, Toyota, European vehicles. It was used quite a bit, went away with OBD1. And the reality is it's still a 3-wire sensor. So at the end of the day, we have a power, a ground, a signal return. The signal return is going to change based on how much air is going in the engine, just as it's going to do with the hot wire I'm going to talk about. The only reason why I talk about the hot wire a little bit more is because it is used by pretty much everybody today. And I'm going to talk about why they fail the way they do and why we clean them. So that's why I want to touch base on them a little bit more. All hot wire sensors use the same basic operating principle, regardless of manufacturer. Sensors use 3 wires for their signal circuit, just like other 3-wire sensors that we have looked at, but may have up to 7 wires at their electrical connector, but only 3 of them are for the sensor themselves. So we can have other switches or other sensors built in. For example, I may have an intake air temp sensor, 2 wires, plus a mass airflow sensor, 3 wires. Now I have 5 wires there. There's 5 wires going to the housing, but it's not a 5-wire sensor. It's a 3-wire sensor. So that's why when I see wires go into something that kind of break the rules, for example, a demo engine that I have on campus, which is a Hyundai, has 4 wires going to the map sensor. Well, wait a minute. I only need 3 wires for a map sensor. Well, that 4th wire is for the intake air temp sensor, and it shares the ground with the map sensor. So the ground is shared between the 2 sensors. I still have a 2-wire sensor and a 3-wire sensor. They're just sharing a ground wire inside the sensor. So it's, you know, at first glance, it looks like it's breaking the rules, but when we see something that at first glance breaks the rules, wait a minute, let me go back to how these things work. Now let me look at the wiring schematic and see what they did. Because manufacturers do stuff like that all the time. And that's why having these basic rules really helps us understand what has to be going on and not treat it like it's this, you know, hey, we need to talk about Hyundai sensors for 10 minutes because this is different. Then we need to talk about Ford sensors because they're different. And no, let's look at our basic rules and then apply them as we see new things. So they have a voltage reference, ground, and signal return wire, although the mass airflow sensors work very different inside from TPS and MAP sensors. On the outside, electrically, they work the same, so many of the same electrical tests apply. So here is a MAP sensor right here, or mass airflow sensor, excuse me, right here, between the air cleaner and the air intake duct. This happens to be on a BMW. And just like with other signals we've talked about, I'd want to use a scope because I want to see it go from, you know, low to high or high to low, whatever, however this thing works. I want to see that signal change, and I want to compare that signal against manufacturers. And so in order, since I'm measuring air coming in the engine, unlike the TPS that I'll measure with the engine off, I have to measure this with the engine running, which means I need to snap the throttle very fast and let go very fast so I can get a big gulp of air in and then see how the sensor responded. And that's exactly what I did here. So here again, I have a 5-second time base and a 5-volt scale for my amplitude. So at idle, I'm about 1.6 volts. And when I snapped the throttle, I went to just over 4 volts. And came back down. And this is a known good sensor. Mass airflow sensors, hot wire sensors should go over 4 volts when snapped. Now, if you notice our pattern here, it comes up, it dips down a little bit, and then goes back up again. This is not a dropout. This, unlike our TPS, which is just measuring an electrical signal, because I'm moving it constant, here, this is an electrical signal based on the air coming in the engine. Well, when I first open the throttle, I get this big gulp of air into the engine. But my engine isn't spinning fast yet. So as my engine has to start spinning, I've brought more air in than I need. So the engine has to start spinning. So now that I did the initial dump, I opened that throttle really fast. Now the air rate has slowed down a little bit till the engine starts to catch up. Now that the engine is caught up, now we're going to continue climbing. So this is not an electrical dropout. This is that we're measuring the air coming in, and the air that's coming in slowed down for a split second as the engine had to catch up with all this new air coming in, because the air can move faster than the mechanical function of the engine can. So there's a little bit of a lag there, and that's what we see. And so this is all very normal. And what do we got here? We probably, if I drew the cursors, that's probably all of about 200 milliseconds that happened. So now if we compare this with a malfunctioning mass airflow sensor, in this case, I got my initial snap. We can see where it dropped down, waiting for the air to catch up. And then it ramped up, and I barely got to just over 3 volts. I didn't come nearly to that 4 volts, and my initial rise wasn't good. So what happens with mass airflow sensors, because this is a hot wire sensor, what we do is we send current down this wire to maintain a certain temperature. As air blows past it, it cools the wire. So the more air that blows past, the more current we have to flow through the wire to keep it hot. When mass airflow sensors go bad, often it's because they're dirty. Well, if I have a wire that I want to keep hot, and now I put a nice barrier of dirt around it, and this air is coming through and blowing on this dirt, my wire has a nice blanket, so it doesn't take as much current to keep the wire hot, so it underestimates the amount of air coming in because the wire is insulated by the dirt. This is why a bad mass airflow sensor can set a lean code or a lean adaptation code, because the computer is under measuring the amount of air coming in the engine. And if it under measures the amount of air, it's only going to put in the fuel for the amount of air it measured. Now there's not enough fuel for the engine. The computer system's unhappy. It detects a fault and sets a code for the car not having enough fuel in its mixture. This capture right here is off a car that had a code and was bad that I had in the shop.
So what would you do with that? Just clean the.
By the time they get a code, they get a new one. They get replaced. Now we do clean these as part of preventive maintenance. Normally, if I'm doing a major service, they do make a special mass airflow sensor for cleaning them. If you're tight on the budget and you have one that's bad, you can try cleaning it, and many times it'll get it back to life and get the check engine light to stay off. The reason why we don't do it on customers' vehicles is, first of all, I need to warranty it for 224.
Okay.
The other issue we have is that it's not going to bring it back to 100%.
Okay.
So, for example, and I played with this some, because I mean this is kind of an ethical issue, right? Are you replacing something that could be cleaned and the customer's not getting any additional benefit? And so we have a way of measuring what's called the volumetric efficiency of the engine. That's the engine's ability to breathe, which also measures the mass airflow sensor function. And so I had some vehicles that would set a code, test bad like this. I'd measure the volumetric efficiency and it'd be in the 50 or 60% range. I'd clean it and I'd get up to about 80%, which is in the acceptable range, and it would no longer code. When I put a new one on, many times I'm now up in the 90-95% range of efficiency.
Mm-hmm.
So there's a big difference there. So if I'm at 80%, how long is it going to be before I'm down under 75 when I could have a problem? Versus having something new at 95. And obviously there's other stuff that causes issues in, 100 and something thousand miles that can create an issue. So for me, I will clean mass airflow sensors for maintenance, which helps keep them from failing and keeps cars running great. By the time it gets to the point of turning a check engine light on and the customer comes in for a problem, it's going to get a new one. I may clean it as part of the testing process, but it's going to get a new one before it leaves as a recommendation. The customer can always decline that and say, no, can you just clean it? Can you do that? Yeah, we can try it. And hey, we can see how it goes. And but that way, if the car comes back in a month or 6 months with that same problem, it's not my problem because I recommended the complete repair.
So in the case of cleaning it on a regular basis for maintenance, would you do that every time maybe you change the actual filter, the air filter in the car?
About every 30,000 is fine.
Okay.
Yeah.
And so that's something to maybe look for, like if you're in a really dusty area too, right? Where you got a lot of
dirt. Yeah, because we live in a dusty area. So every 30,000 miles, that air filter is pretty done. But this is also why K&N air filters create an issue. Because the dirt that passes through the K&N will collect some oil, or can collect some oil, and then allows it to stick to the mass airflow sensor prematurely. So we see some issues with that type of product with an oil bath air filter on mass airflow sensor system.
Yeah. Okay. It's almost like plaque inside of the arteries getting to the heart, huh? Sending an electrical signal. A car is like a body.
Yes, it is. So a Hotmeyer mass airflow sensor circuit works just like a TPSN map from the outside of the sensor to the PCM. Is that true? That's true. A mass airflow sensor can be tested on a lab scope just like a TPS. Is that true or false?
True.
True, I just showed you. So here's my 3-wire circuit. So I have a PCM signal input. Remember, this is the same PCM top and bottom. I've got test points at the sensor, power, ground, signal return. Usually the sensor is the easiest thing to get to, so we test there first. If I have 5 volts between here and here, there's no reason to test it at the computer. If I don't have 5 volts between here and here, now I need to go to the computer and test to see do a voltage drop to see what side is my problem. If things are good here, I can use the test point here for my meter, and then just like I did in the previous PowerPoint, use my scan tool to see what the voltage is that the computer sees and compare those two, which again keeps me from having to go pin it out at the computer unless I find a problem. So a lot of manuals have you go on the computer, finding the pins and doing all the voltage drop checks. If I got all my 5 volts here, I know all this has to be good. If my test point voltage here is the same as what the computer displays on the scan tool, then I know this wire is good, even if the signal is wrong, which means that if I have the wrong signal, it's either a bad sensor or something the sensor is attached to that might be broken. Like I've seen where like an EGR position sensor doesn't work because the EGR valve isn't moving when it's commanded to, right? So I'm getting a sensor code, but it's actually a broken sensor or vacuum line. So we need to keep everything in perspective. So when I'm testing the sensor, I need to make sure whatever it's measuring is actually changing condition, whether that's pressure or position or whatever. And then we do have all of our test points. But you can see how understanding how the circuit works means that I don't need to go test the computer very often, which saves me a lot of time. Computers are hard to get to. It's hard to see when there's 100+ little wires going to it. So if I understand that this is a series circuit, this is my only load, and it has to use all of the 5 volts, and it has all the 5 volts, that means these wires have to be good. And if my signal return is the same as what I'm getting at the powertrain control module, then it has to be okay. So that works easier for TPS than it does for something like, or MAP, which will give me a voltage, then maybe mass airflow, which may not give me a voltage. It may, depends on the manufacturer. But again, it just allows me to, what do I really need to test? Don't just blindly follow the instructions that say, oh, measure the resistance in the wire between here and here. Well, why would I do that if I have all my 5 volts? What a waste of time. Now, if I only have 4 volts, okay, then someone stole a volt. Now I need a voltage drop the power and the ground side and see where my problem is. Keep in mind, my 5 volts is shared and my ground is shared normally by all my 3-wire sensors. So if I have codes for 3 sensors that are all 3 wires and all their voltages are low or all their voltages is high, I need to suspect that maybe I have a problem with my VREF or I have a problem with my ground, depending on whether they're low or high. Because what are the odds you got 3 bad sensors on a car that all use 3 wires that share all the same stuff and you have 3 problems? Probably not. It's probably one problem that's affecting all 3 things. So if we compare our 2-wire to 3-wire, so here I have test points on my 2-wire sensor. I'm measuring the voltage drop across the sensor, which is going to give me the same reading as between this wire and ground, theoretically, providing this ground is good. So I always want to do a voltage drop check on that ground. PCM input. And test points over on the 3-wire sensor. Again, going between signal return and ground, just like I went between signal return and ground. So I'd have 0 volts here, 0.5 to 4.5 volts there on my signal return. On my 3-wire sensor, I'm going to always have 0 volts there. I'm going to always have 5 volts here, and I'll have between 0.5 volt and 4.5 volts on my signal return wire. So just a quick comparison of the two. So an NTC type sensor, the resistance goes up as the temperature increases. Is that true or false?
False.
False. It's an NTC,
False.
right? So NTC, high resistance cold.
Okay.
When testing an NTC type sensor for proper voltage level of the signal, the positive lead of the DVOM should be placed on the signal wire and the negative lead should be placed on sensor ground. Is that true or false?
Is it the reverse?
Well, what am I checking? When testing the NTC type sensor for proper voltage level at the signal, the positive lead of the DVOM should be placed on the signal wire and the negative lead should be placed on ground.
True.
That would be
True, I
true,
get-
right? Because that's going to show me my 0.5 to 4.5 volts.
Okay,
When testing a three-wire sensor, there should always be a reference voltage applied by the computer to the sensor.
true.
True. The signal voltage of a two-wire sensor is always measured on the wire between the internal resistor of the sensor and the PCM.
True.
True, right? We're measuring that wire because it's a series circuit, two loads. I'm just measuring the voltage change on that wire in the middle. When testing a three-wire sensor, the technician should always read a minimum of 0.5 volts on the ground side of the sensor.
I think that's true. I don't remember the exact number. Always?
Well, yeah, first warning should be always. But
Yeah.
the other is, what should I always have on the ground side of the sensor? 0 volts.
Zero.
Zero, that's what
Right?
that's what I was thinking.
Whether it's a two-wire or a three-wire, because if I have anything other than 0 volts here, it's using some of my voltage, which is going to change the accuracy of my signal return on either style of sensor.
Okay, so that's false.
That's false.
Yeah.
Because if I have high resistance on the ground and I'm using voltage here,
Right.
it's going to change my signal return voltage.
Okay. Yeah, I was iffy about that. I remembered that number, but I wasn't. I couldn't remember in my head that little ballpark. Okay, I got it.
No worries. That's why I went back, and that's why we have the questions. And this is a tricky question because, wait a minute, should I what? No, ground, I better have 0. If I don't have 0, I don't have ground.
Okay.
And actuator circuits. So tomorrow, we're going to get into actuator circuits. I will turn some sensor labs on for you guys. I got a couple videos I did. Hope you enjoy them with the lab sheets. And tomorrow we'll look at actuators. And that'll probably take the whole time tomorrow. I don't think we'll get to engines tomorrow. We'll probably get to engines Wednesday. Because we're going to not only look at actuators, but also control circuits and how we test it. So the actuators themselves are pretty straightforward, but how we control them gets a little more complicated. So I'm going to spend a little time on that. So on that note, if anyone have any questions before we call it a day?